the method can also be applied in the frame structures. So here I will have a brief discussion about the use of slope diffraction equations and then apply to the so-called frame structures. Now, if you still remember, when we have the so-called calculated diffractions, we can actually also apply to the frame structures as well. Now for frame, actually there will be two kinds of frame. One we call that it is with sideway. That means when you apply the load, then it will deform laterally. Or actually there's another one which called the frame with no sideway. And then the method of analysis, there's some difference between the one with sideway and then without sideway. But for a frame, actually, if it is without sideway, means that actually it is properly restrained. But as you can see from the left-hand side, if there is a fixed support and then to restrain the members or restrain the frame from deform laterally, then we can call that it is a frame with no sideway. So you can see that for the first two samples, actually there are supports to restrain the frame to deform in lateral direction. So for the first two we call that they are also the frame are actually a frame without sideway, because you can see that they are restrained, which restrict the frame to deform laterally. Or actually you can see that if the frame itself is symmetrical and then the loading is symmetrical, then actually the frame will just deform symmetrically, and then they will not deform laterally. 即係佢唔會歪埋一邊啊，唔會向左或者向右歪埋一邊。Then we call that those kind of frame again as the frame with no sideway. Okay, that means it just have some vertical deformation, but without lateral deformation. So for example, if you have a frame like that, if you have a triangular load applied at the frame member BC, and then you will only deform vertically, okay? And then for this case, we don't count these support deflections. And then you may just write down again the member ends moment equations for member AB, BC, and the CD. So again, you can write down the member end moment, MAB, MBA, MBC, MCB, MCD, and MDC for these frame structures, okay? So it is just like a continuous beam, just like what we have done before. So they are quite similar. And as you can see that there is a triangular load at the member BC, so there will be fixed end moment. If it is a triangular load, just for your information, if you have a fixed end or fixed beam on both sides, and then you have a triangular load for this arrangement, then say for example you have W here, and then you will have fixed end moment on both sides. Actually, it is equal to 5WL squared and then divided by 96. 5WL squared and then divided by 96. And then you have the length in between. So on the left-hand side, you have the fixed end moment, 5WL squared over 96. If you substitute the values for W means here is equal to 24, and then the length is 8. Then this is 24. And then this is the length is 8 meters. Then you can find that the fixed end moment on both side, left-hand side, and then the right-hand side is equal to 80. Now remember, because actually we will treat clockwise moment as the positive, so because the fixed end moment here is counterclockwise, so it is a negative value here, okay? Because it is counterclockwise, this is clockwise, because this one is clockwise, you can see that. So you will have a 5WL squared over 96, which is equal to 80 kNm on the left-hand side, negative 80 kNm on the left-hand side, and then 80 kNm on the right-hand side. And then you can see that all the angle, theta A, theta D, they are on the fixed support, so the angle of rotation is equal to 0. However, you can see that for the A, for the B, and then for C here, actually you will have rotation at this joint. So both theta B and then theta C are not equal to 0. So you can write down the equation here. Now remember, this one is just the bracket. For the PowerPoint, sometimes I don't know why it cannot show the so-called bracket. Then you can still use the equation 2EI over L, and then 2 theta N is the near side, theta F is the far side rotation, and then phi is actually the deformation of the support. And then for the frame without sideway, then the phi is actually equal to 0. And then include the fixed end moment. So you can write down MAB, MBA, MBC, MCB, MCD, and MDC expression here. Now you can see that both theta A and theta D are equal to 0, but just theta B and theta C are unknown. So you can see that you have theta B and theta C in these 6 equations. In other words, we just need to find the theta B and then theta C, and then we can find all the member end moment. Okay, so how can we find theta B and then the theta C? Again, we just need to take a look at the joint here, and then you need to know MBA plus MBC must be equal to 0. This is the first equilibrium equation. And then you need to know MCB plus MCD must be equal to 0. So you can use these 2 equations. MBA is here, MBC is here. So you substitute these 2 to the 2 equations. And the MCB, MCD are here. So you just need to substitute this into 2 equations. And then you use 2 equations and 2 unknown. And then you can solve for theta B and then for theta C. Then you can find for the answer. So you use these 2 equations, and then you can have these 2. You can see that theta B, theta C, and theta B here. So you use these 2 equations to find for the answer. And then after solving those 2 equations, you can find that theta B is equal to negative theta C, which is equal to 137.1 over EI. And then you can substitute theta B and then theta C back to the equation. And then you can find for the member ends moment. And then from the member ends moment, you can find for the moment diagram. Okay. Now for the frame actually with sideway, that means the loading may not be symmetrical, or there is no constraint to restrain the frame to deflect laterally. Then we call that it is the frame with sideway. Now a slope deflection equation can also apply to this kind of frames, but it will involve more procedures. So you can see that for here, if you apply the load, say for example, you have applied the load P, but not in the center. That means the loading itself is not symmetrical. Then actually the frame will deform laterally, okay, laterally. And then you can see that there are actually deflections on both of the joint B and then on the joint C. When you write down your equations, I mean slope deflection equation, you have to include these deflections. So for the member AB, I mean moment MAB, and then for the moment MBA, you need to include this delta. And then for the member end moment CD and then the DC also, you also need to include this delta. So we will have an additional unknown, which is actually due to this deformation. And then we need an extra equilibrium equation to include so that to solve for this delta. And then I will illustrate these solutions by using an example. For here, you can see that we have a frame and then I have applied load 200 kN applied at the joint B. Then you can see that I will have a delta at the joint B and then have a delta at the joint C. Now again, I can write down the member ends moment equation for each of the member, like MAB, MBA, MBC, MCB, MCD, and MDC. So I can write down 6 equations. Now, for the find AB here, that means actually it is the delta divided by L. Delta is this deformation, and then L is the length. And then you can see that actually it is equal to delta divided by 4, okay? And then for the member MCD, you can see that there's delta and there's the length here. And the phi actually is equal to CB maybe. It's actually equal to delta divided by L again, so it is delta divided by 6. Now actually we have two, I call that phi AB and phi CB. And then I actually want all of them actually are in terms of DC. I just want to, in terms of, sorry, this is CD, not CB. Find CD is equal to find CD, find BA is equal to find AB. Now I just want all the things in terms of phi DC. So you can see that phi AB is actually equals to delta divided by 4, while if you can take a look to these two, phi DC is equal to delta and then divided by 6. So you can see delta is actually equal to delta and then times phi DC here. I just substitute this one because you can see that this one and then this one, they are equal, right? So 6 times phi DC is equal to delta. So I can say that phi AB is equal to 6 over 4 delta phi DC. So when I write down the equation, you can see that this is 2 EI over L. Then this is 2 theta A, because theta A is a fixed support, so theta A is equal to 0. While theta B is an unknown, so I will just leave it here. And then for this one, the delta, this one is actually phi AB. But I have just shown you that phi AB actually equal to 6 over 4. Phi DC will actually write it here. So I will reduce to this equation. And then again, for MBA, again 2 EI over L, and then theta B here. I know that theta A is equal to 0. And then this 3 phi and phi is equal to BA. BA is actually equals to, again, the AB. So it is still equal to 6 over 4 phi DC. So I have this expression here. And then for MBC, actually, there's no diffraction. Now, this diffraction, it only belongs to MAB, I mean member AB. And then for the right-hand side, the diffraction only belongs to the member CD. But for the member BC, there's no diffraction. So we will have no diffraction here. And then no fixed end moment, because there's no loading applied. And then I can write down the remaining equation 4, 5, and 6. And then again, to solve for the unknown, because I have theta B and theta C, I can use the 2 joints here to solve for the answer. Two joints actually similar to before, because the moment at the member ends when they act together should be equal to 0. So it is straightforward. You just have MBA plus MBC equal to 0. MCB plus MCD again equal to 0. Now, but these two, I can only solve for theta B and theta C as before. But don't forget that right now I have an additional equation, which is, additional unknown, which is find DC. Then if I have just two equilibrium equation at the joint, then I still cannot find the unknown find DC. Then I need one more equations in order to find this unknown. Then actually I will consider the equilibrium of the member. Now you can imagine I have the force here. This is the first, my frame structure is something like that. I have 200 apply here, and then at here I will have my VA, and then here I will have my VD, sorry. So 200 minus VA minus VD is equal to 0. So I will use summation Fx is equal to 0, and then to find for that. And then from the member, actually you can see that my shear is on both sides, while MBA, MAB are also on the ends of the member. Like the values of VA actually is equal to the sum of the moment, MAB plus MBA, and then divided by the length, and then I can get the shear force at the member ends. So I will use MAB and then plus MBA, and then divided by 4, and then I can get the shear VA. And then for the member CD as well, I will use the moment MCD plus MDC. These two, I add them together and then divided by the length, then I can get the member end shear. So by using this expression, I can substitute back to my original equation. Then I can have this expression, one more equilibrium equations, which describe the moments. Then you can substitute MAB, MBA, MDC, and MCD from previous expressions, and then you have one more equation here. Then you can see that I have defined DC in my equation. So right now, including those two considering the equilibrium of the joint, then I have my third equations. And then from these three equations, I can solve for the values for theta B, theta C, and then find DC. And afterward, I can solve for these three. After solving for these three, I can back substitute to those 6 equations. And then I can find for the member ends moment. Okay. So this is the way how to solve the so-called the sideway frame. Well, actually, the method can also be extended to a multi-story frame, as you can see here. We have delta 1, and then at the upper level we have delta 1 plus delta 2. Now this one is more complicated because you can see that we have quite a lot of members. If you can count, we have 1, 2, 3, 4, 5, 6. We have 6 members. And then there are actually the delta for the member AB, delta for member BC, for ED, and then for EF as well. So for this one, we can write down the slope deflection equation for 6 members. So we have totally 12 slope deflection equations. So it is something look like this. So it is quite a lot. And then you can see that actually you will have find 1 and then you have a find 2. Actually, it is just the deflection divided by the length of the member. And then you can see that we have unknown theta B, theta E, theta C, and theta D. They are actually unknown, while theta A and theta F are equal to 0. Okay. To solve for these 6 unknown, because delta 1, delta 2, and then 4 rotation at the joints are the unknowns, we can use 4 equilibrium equations at the joints. So we have 4 equations, but we have 2 left. We need 2 more. Then again, we can consider the equilibrium equations and then to have 2 additional equations. So first of all, of course, we will have 5 equilibrium equations, 4 equilibrium equations at the joint. So you can see that we can have MBA plus MBE plus MBC is equal to 0, MCB plus MCD equal to 0, MDC plus MDE equal to 0, and then MEF, MEB, and MED, when they acting together, again equal to 0. Okay? And then actually we need 2 more equations. For here, again, we can use the equilibrium equation. We can again use summation of fx is equal to 0. Sorry, here again, there's some error in displacing some symbols. Now, you can think of the equilibrium for 2 parts. Actually, you can think that for the first part is here. This shear, and then we balance this 40 kN. And then for the second part, actually, you have the shear on the first and then second floor, 40 kN and then 80 kN. And actually, the shear here will again balance these 2 forces. So we will consider the equilibrium equations by summation fx is equal to 0. So you can see that 40 minus VBC minus VED is equal to 0. And then the second one is 40 plus 80 minus the shear on those 2 columns, again equal to 0. Then remember, actually, the force in the member plus the member end's moment divided by the length is actually equal to the shear. So again, we have 2 additional equations which relate the moment in the equations. And then we can substitute the expression from the previous equations, I mean from the moment equations. And then you will have 2 additional equations. So totally, you will have 6 equations to solve for 6 unknown. Then once you find all the values, you just substitute back, and then you can find the member end's moment. Now for this one, actually, it is quite tedious because you need to solve for 6 unknowns by using 6 equilibrium equations. Basically, it is difficult when you are having quite a lot of deflections for your structures. So it is may not be preferable for sideways frames. Okay. For this one, don't worry too much because for this one with the sideway, actually we will not consider, or we will not put it in the exam because the workload will be too much, okay, for the examination. We will only up to for the frame without sideway, okay? So don't worry too much for that. Because those with sideway, we may just include that in your assignment, but not in the examinations. Okay, so is there any question before I go to the next chapter? Okay, so for this one, actually, you have learned one more method to solve for the indeterminate structures. And then today we will introduce one more method, which is actually a very powerful method to solve for, again, for the indeterminate structures, again, for the member end's moment. For that one, actually, it is a very, very easy one, because actually it is an approximate method, but it is actually still accurate, and it depends on how much round you will perform for your analysis. Again, it is for the continuous beam, or it is for the frame structures. And then actually it is very famous before, and then actually it is widely adopted some years ago. So the name of it is called the moment distribution method. Okay, so tonight we will talk about a new method which is called the moment distribution. So we will talk about the general principle and then the definition, moment distribution for beams, and then the moment distribution for frame without sideway and those with sideway. So first of all, we'll talk about some general principle. Well, actually, moment distribution, I can say that actually it is an approximate method. And then actually it involves the so-called the iterations. That means you need to perform the analysis for several times before you can get a close answer to the exact solutions. It is an approximate analysis, but the accuracy will increase if you perform more times. And then actually you can control the accuracy by yourself if you keep carrying on the analysis. Now for this method, actually it is widely used before the invention of the computer. Because right now, if you have computer, then actually you can solve for the matrix without difficulty. Then actually that means before, as I mentioned, you need to solve for the equations if you have many deflections or you have a high degree of indeterminacy. But right now, the advantage is that when you have a computer, actually it is easy for you to solve for a matrix with high degree. Say for example, I think it is good enough for you to solve for 3x3 matrix, right? But with a computer, you may be able to solve for 1,000 by 1,000 matrix. It is much quicker because computer can help you for that. But for this method, actually, it is widely used when there's no computer. And then actually it is a very manual method. Then you can solve for structures with very high degree of indeterminacy. And then for this one, actually, the calculation is relatively simple. It does not involve any integration or differentiation, something like that. It is a kind of procedures-wise only. So it is considered as a very powerful method and then a very easy method. But there are actually some steps that you need to follow, and then you can solve for the answer. Now, for this one, actually, assume that you will have structures of continuous beam. First of all, you will log, for each joint. And then afterward, you will unlock each joint and then distribute the moment within the members. Now for this one, I will try to explain step by step, then I'll let you know how to perform this kind of analysis. So again, sorry for that, this one on the bracket. I just would like to let you know a concept first. For carryover, actually what is carryover? Now, when you have the moment applied on one side of the beam, right here, you can see that there's a moment applied here. Carryover means that there will be moment on the other side of the structures. Say, for example, if you have M apply the moment and then you allow it to rotate, then actually there will be a moment theta A, as you have learned for your slope deflection equation. And then the moment on the other side is actually half of the moment. Say, for example, M is here, then this M dash here is actually 0.5 M. That means half of the moment. Then if you have moment on the left-hand side, you will carry over the moment to the other side. We call that the carryover. That means you will transfer the moment from the left-hand side to the right-hand side. We call that the carryover. And then usually carryover is in the a factor of 0.5. And that is plus. That means if it is clockwise or counterclockwise, then the carryover moment will also be in the same direction. You can see in this example, M is in the clockwise direction. If you apply the moment at the joint A, then actually you carry the moment to the side B. And then the magnitude will be 50% of that one applied at the joint A, okay? And then right here, you can see that I have a T member here. I think you have some impressions for this one. Actually, it is quite similar to the one in the tutorial, right? Now, right here, you can see that you have 3 members connected to the joint A. Now, I ask you one question. If you apply a load at the joint A here, say I have applied 100 kNm here, then I ask you how much moment will be distributed to the joint, to the member AD, how much will be distributed to the member AC, and then how much will be distributed to the member AB. Now, here actually I have 3 member N moment, MAD here. I have a MAC here, and then I have a MAB here. That actually how much moment will be distributed to the member AB, how much moment will be distributed to the member AC, and then how much moment will be distributed to the to the member AD. Well, actually depends on the stiffness of the members. I just make it as an example for analogy, saying that if you are having $100, okay, and then it is going to distribute by 3 people, okay, then how to distribute the money among the 3 guys, okay? And then I can say that the guys who is very strong. For the guy A, he is very strong guy. And then the B is medium, not very strong. And then the third one is weak. Then of course the strong guy actually because he is strong, he will take most of the money. Okay, because I'm strong. Okay, I will occupy and I will try to get most of the money from all those, okay? So he will get more. The strong one will get more. And then the weak one will get less, okay? So it is a very normal to think it is actually the same approach is applied to our structures. But because actually the 3 members, they are connected in the same joint, the strong guy or the strong member will take most of the moment, while the weaker member will take less moment. So how to define the strength of the member or the stiffness, we call that, of the member, so that you will know which one take more moment? We will use the so-called the stiffness factor. We define it as 4EI over L. E is the Young's modulus, I, of course, is the moment of inertia, and then L is the length. If the Young's modulus is larger, then the member is stronger, okay? If the I is larger, that means for the shape, so that the I is larger, that means the area is further away from the centroid, then we call it the I is stronger. And then if the length is shorter, then all this factor actually makes the member more stiff than the others, stiffer than the others. Then the K will be larger. So for here, actually, we can count on this so-called the stiffness factor. Then in order to know which one is stronger, we will first of all consider the total stiffness of the 3 member. Then we just add all the members together, the stiffness together, and then we have the values of 10,000. And then well, we can know how much moment will be distributed by using a so-called distribution factor. You can see that actually we have the summation of k, and then the k divided by summation of k. Say, for example, you have 4,000, and then the total is 10,000. So this is, we call it the distribution factor to the member AB. So that is 0.4. That means if I have a total of 10,000, and then the member AB actually have 4,000, that means 40% of the stiffness actually is contributed by the member AB. That means if I have a moment applied to the joint, 40% will goes to the member AB. If I have considered the member BC, or I mean the AC, it is equal to 5,000 and then divided by 10,000, and then it is equal to 0.5. Then if I have a moment applied to the joint A, 50% will be distributed to the member AC. And then finally, I have a member AD. Then you can see that it is equal to 0.1. That means if I have a moment applied to the joint A, 10% will be distributed to the member AD. Okay? So, as you still remember, our method is called moment distribution. So it involves the distribution of the moment at the joint to the members. So you can see that depends on the stiffness of the member, then the distribution will be different accordingly. And then basically for the K, actually, before we mentioned that it is 4EI over L. But usually for the same truss, actually, the E are usually the same. And then actually we can use the so-called relative stiffness factor to consider our distribution factor. So instead of using 4EI over L, we can just use I over L. Because in most of the cases, actually the frame will be using the same material. It is not very common to use different materials. Say you have one member using concrete, one member using steel, one member using glass. But actually it is not common. So we may use I over L as the stiffness factor and then consider. And then for the moment distribution of the beams, we will describe the procedure here. Now I will use a beam here to illustrate the idea. You can see that I have a two-span beam, IB and then the BC here. Then on the left-hand side, there's no loading applied on the top of the beam. And on the right-hand side, I have a distributor load applied at the top of the beam. Then actually, first of all, I will try to calculate the distribution factor at the joint B. Saying that if I have a moment applied at the joint B, then how much will be goes to the joint, to the MBA side, and then how much will goes to the MBC side. Because I will use this concept afterward, so you just take a look first. If I have a moment applied at joint B, how much will go to MBA, and then how much will go to MBC? And it actually depends again on the distribution factor of BA and the distribution factor of BC. So first of all, we need to calculate the stiffness factor for the member BA. So it is 4EI over L. So you can see that 4EI over L, L is 3 meters. And then I is 120 times 10 to the power 6. So actually it is equal to 4 times 40 and then times 10 to the power 6. While KBC is equal to 4E over 60 over 10 to the power 6. So the distribution factor on BA actually is the K on the BA divided by the total K. So it is equal to 0.4. And then the other side is actually equal to 0.6. That means if I have a moment applied to joint B, which is equal to 10, then 4 will go to BA, and then 6 will go to BC, okay? That means it will distribute into 2 moments. And then for the distribution factor for the fixed support, actually this is infinity. This is infinity. But say, for example, if I have a joint, have a moment applied here, then theoretically I should have moment in the member and then have the moment in the wall. Okay, if I have a moment applied here, then it should distribute some in the member and then some in the wall. But you know that actually the wall have infinity stiffness. We assume that the wall is rigid. And then the moment or the stiffness is infinity. So in this way, actually, you can see that the stiffness of the wall is infinity. So actually, no moment will be distributed to the member end. So when there's a moment applied at the wall, there's no member end moment. All will be distributed to the wall. So for here, first of all, we will take a look how to find the member ends moment by using moment distribution. Now, if you still remember, our original member is fixed on the joint A, and then I have a member here, and then I fix at the joint C. And then I have a pin support here at the joint B originally. To apply the method of moment distribution, first of all, I will assume that this one is a fixed joint. Assume that it is a fixed. If I assume that it is fixed and then I have load applied on that, then fixed end moment will be developed. But this is assumption. It is originally pin support or roller support. But right now, I assume that it is fixed. I assume that it is fixed. So it will develop member ends moment or fixed end moment. It is equal to 18 Newton M. And then on the right hand side, also equal to 18 Newton M. The question mark is just a dot here. That means Newton times beta. Negative means that actually it is counterclockwise. And then clockwise is positive. So this one is the WL square over 12 and then WL square over 12. So fixed end moment will develop on both sides. However, actually this fixed end moment originally it does not right here because actually this support is not fixed end. We just assume that it is fixed only. Okay, we just assume that it is fixed only. So in order to correct this, actually we will apply the 8000 kNm here in order to balance the original negative 8000 here. Okay, because it should not be here. And then we assume that we apply 8000 Newton meter at the joint B in order to balance the fixed end moment. Okay. So we want to correct that by apply the moment at the joint B because originally it is not a fixed joint, right? To correct that, we just apply the counteracting moment in order to eliminate this fixed support moment. Okay. Okay, once we apply this 8000, and actually, if you still remember, if I have a moment applied at the joint here, then I will go, the distribution factor is 0.4 on one side and then 0.6 on the other side. If I assume I have 8000 applying back, And actually 40% will go to the left-hand side, and then 60% will go to the right-hand side. So 40% is actually equals to 3,200 kNm, while on the right-hand side is equal to 4,800 kNm on the right-hand side. So this moment will be distributed in the two. One is a 4,800 on the right-hand side, and on the left-hand side is equal to 3,200 kNm. Okay. So right here, these two moments will apply at the member ends. Then don't forget that we have mentioned if I have a pin here and then I fix here, if I apply a moment here, then I will induce 0.5 M at the ends. We call that it is the carryover moment. So if you have 4,800 here, then I will carry over 2,400 to the other side. And then I have 3,200 on this side, and then I will carry over 1,600 on the other side. This is recorded the carryover moment. So right here, I have the 8,000, and then it becomes the 2, because actually we'll distribute between the two. And then don't forget that originally I have 8,000 Newton meter moment right here. It is because actually at that time I will have a fixed end moment right there. But in order to eliminate this 8,000 moment, I need to apply a clockwise moment, 8,000 right there, in order to make it to be in equilibrium. But once I apply the 8,000 right there, and then 3,200 will be applied to the left-hand side, and then 4,800 will be applied to the right-hand side. Okay. And then for that one, actually, you will distribute 2,400 to the right-hand side, and then you will produce 1,600 to the left-hand side. Okay. And then for here, then you just add them together. On the right-hand side, you have 8,000 and then 2,400. So you just add them together. And then right here, originally there is no moment, so it is equal to 1,600. And then so here, we will write it in this kind of format. First of all, you have the join here, because you have join A, you have join B, and then you have join C. And then the join A, actually you have AB here for the member AB. And then the join B here, I just write down the join again. So A here, you have member AB. And right here, you have member BA. And then this is join B. And then on the right-hand side, you have member MBC. And then at last, you have CB, okay? The distribution factor actually is 0 at the for the member AB, because all the moment will be absorbed by the wall. So actually no distribution factor is allocated to the member ends AB. And then for the BA and BC, you can see that 60% will goes to the BC, while 40% will goes to BA. So right here, first of all, there's an 8,000, which is negative here, applied at the ends, and 8,000 apply at the member ends CB. In order to balance this moment, we need to add back 8,000 in the joint B. If you add back 1,000, actually you will make the moment 3,200 on the left-hand side and 4,800 to the right-hand side, the joint. And then don't forget that this one will distribute the moment, half of the moment to the other side. Then actually, once you do like that, actually all the joints are in equilibrium. And then you just add all of them together. And then you can get the answer, 1,600, 3,200, and then negative 3,200, and 10,400 here for the member ends moment. Again, positive means clockwise, so you can see that this is the clockwise moment. Clockwise moment. And then Counterclockwise means negative, so you have negative. You have positive here. Okay. So this is how you can get your member ends moment. It is very quick and very convenient. Okay. So it is a very simple and then quick method. Okay, for your analysis. Let me illustrate one example for you, and then you can know the powerfulness of this example. Say, for example, you have a beam like that. This is A, B, C, and then a D. Okay, again, you will have the fixed end moment like that. And then you will try to find the so-called the member ends moment. In order to make it simple, I will just make it to the same length here. Actually, they can be in different length, but in order to make it simple, I will just use one here, and then assume that I have a distributed load here, and then I have a point load here, or maybe just a distributed load here. Okay, and then I have 5 kNm. Then I want to find the member ends moment. Now, of course, you need to find the distribution factor. BFBA is how much moment will distribute to the BA side. Now, actually, you will use I over L. For the side AB, and then for the side BC. And then you know that all of them are equal to 1 over 10, because assume that all the I are the same. So you can see that DFBA is equal to 0.5. So to the BC is actually equal to 1 minus 0.5, so it is still equal to 0.5, okay? And actually all are equal to 10 meter, so the distribution factor for CB will also be equal to 0.5, and then the distribution factor for CB will also be equal to 0.5, okay? So from here, you have calculated the distribution factor already. That means when there is a moment applied at the joint, 50% will go to the left-hand side, 50% will go to the right-hand side. And then for the fixed end moment, actually there's fixed end moment for the member BC, which is equal to WL squared over 12. W is equal to 5. Then length is equal to 10 and divided by 12. So here I can just calculate and take a look. Let me calculate for you. Five times 10 square divided by 12. It is equal to 41.67. While FEM for the CB is equal to 41.67 as well. So this one is quite straightforward. Is it okay for you? Okay. So for this one, you have your fixed end moment and then you have your distribution factor. So in order to find for the answer, first of all, you just follow what we have done before. For the join here, we have join A, B, C, and a D. And then for the member here, we have join AB, BA, BC, CB, CD, and DC. So we can write down something like that. And then for the distribution factor, saying that we have 0 here because when it is connected to the wall, actually it is equal to 0. And then we have 0.5 on both sides. And then we have the 0 on this side again because it's connected to the wall. And afterward, well, we have the so-called the quicksand moment. It is actually equal to 0 for those without loading. So it is equal to 0 on both sides. And it is equal to negative 41.67 in the member BC, but it is still 0 on the other side, okay? So actually, if I have 41.7 negative right there, as I mentioned, I need to add back a positive 41.67 in order to balance the moment. So I will have the distribution among the two at the joint. So at the joint B, I need to add back 41.67 to the B in order to balance the moment 41.67. And then 21.67, I will multiply with these two 80.84 on the left-hand side, 20.84 on the right-hand side. Because when I need to balance this moment, I need to add back 41.67 to the joint B. But when I apply 41.67, 50% will go to the left-hand side, and then 50% will go to the right-hand side. So it will be 20.84 on left-hand side and then on right-hand side. But same way, I have 41.67 at the joint C. Then in order to balance the moment, I need to add back negative 41.67. And then 50% will go to the left-hand side, and then 50% will go to the right-hand side. So I have the same value here. And then if I have a moment here, I will carry over 50% to the other side. So I will carry over. Then it is equal to 10.42. And then I will carry over here. Negative 10.42, 10.42. Then I will carry over negative 10.42. And afterward, this is the new moment, new unbalanced moment. I will again distribute my moment. So 50% will go to the left-hand side, and then 50% will go to the left-hand side. And then again, negative 5.21, negative 5.21 in order to balance the moment. This is the distribution of the moment. And then this procedure will be repeated again. And then 50% will go to the left-hand side, 50% will go to the right-hand side. Carryover will be performed again. So 5.21, you just divide it by 2. 2.61, negative 2.61, 2.61, negative 2.61, okay? Again, this is the unbalanced moment. Again, you can distribute the value 2.61 and then divided by 2. Then 1.31, 1.31, negative 1.31, negative 1.31. Then again, you will carry over 50% to the other side. 1.31 and then you just divide it by 2. Because when you carry over, you just carry over 50%. Again, you will distribute to both sides. Again, you will carry over. You may ask, hey, Simon, when can I stop? Well, actually, you will do it until you have a good accuracy. Now we are almost there. Actually, after carryover, and then we need to distribute again. Then we may stop here. Because actually already small enough, the number. Then we just add all the values together. We will, from the fixed end moment, from this column, starting, and then add until the ends. So for here, you will just have 10.42 plus 2.61 plus 0.65 plus 0.17, which is equal to 14.38 here, as the member ends moment first. And then again, you will calculate the one here. From here, you will add all of them together. So 20.84 plus 5.21 plus 1.31 plus 0.33 and then plus 0.09. So it's 27.78. And then negative 41.67 plus 20.84. And then minus 10.42 plus 5.21 minus 2.61 plus 1.31 plus 55.21 plus 3 minus 0.66 plus 0.33 minus 0.17 plus 0.09. They are close enough, so it is okay. And then you have 41.67 and then minus 20.84 and then plus 10.42 and minus 5.21 and plus 2.61 minus 1.31 plus 0.66 plus 0.33 plus 0.17 minus 0.99 or 0.09. So 41.67. So again, this one is 27.75 negative 20.84 and then minus 5.21 plus 1.31 minus 0.33 minus 0.09. Negative 10.42, negative 2.61, negative 0.66, negative 0.17. $10.42 plus 2.61 plus 0.66 plus 0.17. This is 13.86. So you can find all the member ends moment, okay? Now, when you having the numbers, actually it is 0.0 something. That means it is accurate enough because it, the accuracy up to 1 digit after the 0. I mean 0.0 something is actually accurate enough. You can see that just behind 2 digits. I mean after two digits of the number, there are some discrepancy only, but it is close enough. So if we just stop here, then that means our accuracy should be good enough. Then from here, you can see that our member ends moment is positive. That means clockwise. That means it's 13.86, 27.78. Now for the next one, don't forget that there's the distributor low here. And then negative 27.78. You can just say that it is 78 because it is close enough. This is a 27.78. Then again, for the last one is 13. And then this one is 13. On X6. Because both of them are negative. That means both of them are counterclockwise. Okay. And then actually you can find the shear force and then at the member ends by using the so-called equilibrium equations. Now for the first one, it is simple because it is 30.86 and then 27.78. You just add them together, 13.86 and then plus 27.678. It is equal to 41.64. And then you just divide it by the length, which is equal to 10 meters. then you can find that actually this shear is equal to 4.16 here, okay? Here is also 4.16 kN. And then for the moment here, for the next one, actually you can see that this is a 5 kN here. And then you can see that both of the moment on left-hand side and then the right-hand side, they are the same. Then the shear should be the one balance the moment in between. So actually this one should be equal to 25 because 5 times 10 are 50. So 25 kN on both sides. And then for the last one, actually similarly, you should add to here in order to balance the moment. It is again 4.16. 4.16. Don't forget that actually there's a support in between. And then action and reaction 4.16 and action and reaction 25. And don't forget that actually these are the moment applied on the joint. 27.78, 27.78. So here the support reaction is just the 2, 29.16. Again here is the same. You have 24, 5 on one side and then 4.16 on the other side. And then which is equal to 29.16 kN. Of course, you have moment on both sides. And then from here, again, you can write down your equilibrium equations. I mean, the shear force and then the bending moment diagram. First of all, you will have 4.16 on one side. And there's no shear on this side, and then it is equal to back to 0. Then afterward, you will have the shear of 25, so you will go up for 25. I mean 29.16, you will have 25 ahead. And then again, you will go back because you will go down here, it is equal to 25. And then you will go up here. It is equal to again 4.16. Then you will go back here and then equal to 0. For the moment, first of all, it is equal to 13.16, so it is equal to a positive moment here. And then you can see that it is a negative value because it is a negative value. So you will go down and then goes to a value equal to 27.78. This is the moment here. And then you will go up and then you will have the value here and then you will turn down again. And then finally you will go up and then you will have the values here. And then finally you will have a moment equal to 13.86 here. Do you agree? Let me count some of the values for you. 41.6, 30, 30.xx minus 41.6. And then this is 25 times 5, negative 27.78 plus 25 times 5 divided by 2. This is 34.72. Again, this one is negative 27.78. Okay. So you can immediately draw your shear force and a bending moment diagram. So is it okay for you? So again, this method is actually quite straightforward, and then you can apply to different situations. So actually, the case can also be applied to a member with a cantilever. Now you can see that for this example, we have a member here, MAB, MBC, and then the MCD. Now you can see that there is actually a member ends moment here. Actually, you can see that this one is actually equals to 4,000 and then times 2. So here actually there's a moment is equal to 4,000. And then for here, again, there's a fixed end moment, which is equal to WL squared divided by by 12. And then here there's no fixed end moment because actually there's no loading applied at the top. And then because actually this is hanger, so actually there's no moment will be distributed to the member MBA. So this one you do not need to distribute the moment to the MBA. And then you just have the moment distribution within the member BC and then the member CD. For here, we can take a look. So we have member BC here and the member CD here only. Because for here, actually, when you have moment applied here, then part of it will be distributed to the side CB, part of it will be distributed to the CD. And then when you have a moment here, apply here, the moment will not distribute to the side BA, then it will only remain in the side BC only. So we do not need to calculate the moment distribution factor for the BA and then the BC here. So for here, you can see that we will calculate the stiffness for BC and then for CD, and then we will consider the distribution among this joint only. And then all the moment will remain in the side BC if there's any member moment here. So this 4,000 is always here because this one actually negative 4,000 is always in this size, and then it is due to this 2,000 and then times 2 meters. Now, when we have a situation like that, we will again use the a way in this way to state. Now, for the joint here, you can see that this one is 4,000. Because actually it is in clockwise, so we will put it in a positive. And then for here, on this side, we have negative 3.2. And then for here, this one actually for here, this is 5x7.1. And then finally, this one is 293.6 is actually the result after all the analysis. When you write down your fixed end moment, of course, it is due to this 1,500. Then actually for this distributed load, if you have a fixed end moment like that, this one is the W. This one is WL squared over 12. So W is 1,500. And then times the length is 4. And then you divide it by 12. So actually it is equal to sorry, this one is 4 square. And this one is 500. And then you times 2. This one is 4 square. Okay. So you have it is equal to 2,000. Okay. So that's why you have negative 2,000 here, you have 2,000 here. And then if you need to balance this joint, you can see that for this one, for the B, you have 4,000 on the left-hand side because you have 4,000 on the left-hand side. You have negative 2,000 here. So totally you need 2,000 extra. So you will have negative 2,000 apply at the joint B. Like as I mentioned, for the joint B, no moment will go to the left-hand side. So all the moment will just go to the side BC. And then for the joint C here, actually you have 2,000 on one side only because on the other side there's no moment. So 2,000 actually 0.484 will distribute to the left-hand side while 0.517, 0.516 will distribute to the right-hand side. And afterward, you will carry over the moment to the other side. So you have negative 484 and negative 1,000. And then for here, you have negative 516. So here, again, for this moment, you will distribute among the joint C. But for here, as I mentioned, for the BC side, it will not distribute the moment to the hanger. So all the moments will remain here. So you can see that it remains here. It balances itself. And then afterward, this is the distribution among the joint. And then you will carry over again 50% to the other side. And then on the right-hand side, because actually they connect to the wall, so all the moment will be absorbed by the wall. So you can see that all the moments one distribute to the wall, and then they will not carry over because they have been absorbed by the wall. And then right here, this one actually is just within the member. So actually it is still carry over to the other side. And then again, you can see that you carry on these procedures. And then finally, you can find that it is close to 0.1, and then we can stop here. And then you just add all of them, and then you can see that basically at the same joint, the values are the same. But one, of course, in positive, the other one is in negative. These two are the same, and then these two are the same in order to be in equilibrium, okay? And then finally, you can, depends on these member ends moment, you can find out the shear at the member ends. And then you can draw the shear force and then the bending moment diagram. Okay? Is it okay for you? Okay, so I'm not going to finish all today for this chapter, okay? I will leave some in the next round. Okay, so I will stop my recording first.嗱，呢個方法咧係好straightforward㗎，你可以睇下其實佢冇 啲特別嘅數㗎。最難咧，你係揾個 distribution factor 嘅啫。嗱頭先我都講過啦，喺 hanger 嗰度咧係唔會有 moment distribution 過去嘅，全部都留翻晒喺另外嗰邊㗎嚇。因為呢個 join 係講緊呢個 join 呢個 join B， 佢唔會 distribute 去個 hang overhang 嗰邊嘅，因為個 moment 冇可能 carry over 去嗰邊嘅。咁咧，所以咧就係得全部留晒喺右手邊嘅啫。咁另外 join C 咧就會 distribute 去兩邊嘅。咁你一樣咧咁樣做到尾咧，你就可以揾到個 answer。然後咧將佢由頭到尾加晒咧就答案㗎啦，所以好爽㗎嚇。呢個咧你睇到最難揾個 distribution factor 之外咧，其實全部 carry over 係除一半嘅啫。咁你就可以揾到晒所有 member moment， 所以佢係咁多個方法入邊最簡單嘅方法嚟㗎啦，唔使 moment distribution。我意思係唔使integration， 唔使 differentiation， 就咁計完之後咧，就你不斷咁做 carry over distribution，carry over distribution，carry over distribution。咁你做到越細咧就越準 ，OK？ 就係咁樣。有冇問題？好啦，嗱我會擺第二份功課上去㗎啦，咁就會做埋嗰啲 energy method 啊、force method 啊嗰啲嘅，咁你哋可以試下。咁咧就講多一次，個測驗係19號，咁要翻嚟考㗎嚇。嗱呢個禮拜六即係後日咧，我哋有個 lab 嘅，咁full time 嘅同學咧就做咗㗎啦，咁係 part time 嘅同學未做啦，記住星期六翻嚟啦。咁去BU02。如果大家唔知 BU02喺邊度咧，我會擺張相喺嗰度嘅。其實喺 Ivy 嘅停車場行上一層就係㗎啦。BU02啊，如果唔知道咧，都可以問下啲保安嘅。OK，你喺 Ivy 個大個停車場上去行上一層就係㗎啦。咁記住星期六10點啊。如果你真係翻唔到嘅，咁你都話聲俾我聽，你 WhatsApp 度同我講啦。咁你嗰組咧？最好有人嗱，你哋自己要組班底㗎啦，一個同一個即係你哋要組 group 啊，student group， 大約5至6個同學一組啦。咁係我嚟交個 lab report 㗎嚇，好嗎？如果你未組隊嘅唔緊要，嗰日翻嚟咧你先組啦。專業知做咗 lab 先，10點至1點啊，3個鐘頭內搞掂佢㗎啦，好冇？
Sir，
係。
我想問可唔可以加入我嗰個 WhatsApp group 嗰度啊？我未入。之前你唔係講有個 WhatsApp group 係？
你係邊個同學啊？
係張景雄。
張景雄。
係。
OK，咁你嗰個名係唔係你個？睇下先，你個電話係乜嘢啊？你
9751998嗰個。
等我啊！我想問同學，你哋有冇嗰個？而家有邊個係做過 WhatsApp group 嘅管理員啊？Part time 同學嘅 WhatsApp group 嘅管理員，你哋有冇㗎？冇人出聲住啦，唔緊要。星期六翻嚟順便搞埋好冇？
好啊好啊，唔該阿 Sir。
星期六翻嚟順便搞埋 ，OK？咁有乜嘢咧就話聲俾我聽先。如果你翻唔到嚟啊，成啊咁樣，好嘛 ？OK，咁樣就星期六見啦。OK，星期六見。咁今晚到呢度啦。OK，拜拜。